Okay, we're going to look at another antiderivative problem here. So we're supposed to find the antiderivative of 2 over 1 plus 9x squared with respect to x. So the first thing you want to say is, do I know this antiderivative? And maybe your answer is almost. There's a 2 in there and a 9 in there, that if they were not there, I do know that antiderivative. So the derivative of tangent inverse of x is 1 over 1 plus x squared. This is a lot like that antiderivative, but not exactly that. I have the extra 2 and the 9. The 2 I can manage by factoring out the 2 outside the integral, but the 9, can't really do that without messing up this coefficient. I can't factor a 9 out of the denominator without messing up that coefficient. So, all right, so then u-substitution is maybe what you want to think through here. So u equals an inner function is often something that we try. I'm going to list out some choices for u here. This one's actually a little tricky, perhaps, to think about what to let u equal that works perfectly. So we talked last time about u equals x doesn't do anything but change the letters from x's to u's, so that's not really going to help. I could let u equal 1 plus 9x squared. If I let u equal that, though, I get 18x dx for my du. And the problem is that I don't have an x dx. The 18 isn't a problem, but I don't have an x dx. So this is not going to give me the right du. I could let u equal the whole expression. My du on that is going to require some chain rule or quotient rule. So the derivative here ends up pretty complicated. So that doesn't work either. But for this one, you actually have to be a little bit creative to think about what you might let u equal. And it goes back to what I said at the beginning about I almost know this antiderivative. If that 9 weren't there and the 2 weren't there, I do know this antiderivative. So actually, if I do a little rewriting on this integral and think about fitting it into that form of 1 plus something squared and let u equal that something, then this ends up like the tangent inverse form that we talked about at the beginning. This one you have to be a little creative using some algebra to rewrite the 9x squared as 3x the quantity squared, and then let u equal that 3x. There's not an apparent 3x as an inner function in the original integral. But kind of thinking through these other choices for u and realizing none of those are going to give me the right thing for my du, and going back to, do I know this antiderivative? Almost. If I can force this into this form and then let u equal 3x, we're going to be able to make that one work. All right, so if u equals 3x, then my du is 3 dx. I start matching things up. I have a 3x. All right, I don't have a 3 dx, but I can manage that by dividing through by 3. So 1/3 du equals dx. My dx matches with my dx over here. And then I can make my substitution. All right, so this 2 that's here on the numerator, I can go ahead and pull that out of the integral using that property of indefinite integrals here. In place of the 3x, I'm going to put what that is. So my denominator will be 1 plus u squared. And in place of the dx, I'm going to put 1/3 du. So I can put the 1/3 here in front, or I could pull that outside of the integral. OK, so this is now one I do know. I can simplify the coefficients out front and make that 2/3. And this is now in a form of one I do know. That's tangent inverse of u plus c. And then back substitute for the u. Okay, so one important thing from this example is to understand that it's not always obvious right from the beginning of the problem what to let u equal. And sometimes you have to think through some things that might be a dead end before you hit upon the right thing to let u equal. And so don't be afraid to go through that process and kind of play with it a little bit. Maybe use some algebra, correct algebra, to rearrange the function so that you can then find other things that might help to let u equal.